Hi, I am Cristina Monteiro, researcher at the University of Coimbra and member of the NEXT collaboration. I am presenting novel studies on neutral Bremsstrahlung in Xenon, important for Xenon optical TPCs. Here's the outline of my talk, where I will quickly go through the NEXT collaboration and NEXT-White TPC, distinguish between conventional electroluminescence, the so-called EL, and neutral Bremsstrahlung, show the plots of the observation of non-EL emission in the NEXT-White detector, the dedicated setup we have used to isolate phenomena and study neutral Bremsstrahlung in detail, the waveform method, the results, and comparison with the NEXT-White plot, and finally, I'll draw some conclusions. The next experiment aims at measuring the neutrinoless double beta decay with the Xenon TPC, and I would invite you to take a look at the talks number 199 and 122 in the parallel session for neutrinos number 3. And that session is on 30th of August. And for more detailed information on NEXT, you can see those talks. The NEXT-White or NEXT new detector is the TPC in operation at present in Confront, Spain, and the used amplification method of the ionization signal is electroluminescence. Electroluminescence is an excimer-based secondary scintillation, photons, that are released in the de-excitation processes following a three-body collision, creating an excited atom, followed by an excited dimer. The emitted photons are mainly of the so-called second continuum for xenon gas in the wavelength around 172 nanometers. The excitation threshold, that is the electric field above which electroluminescence occurs, is for xenon around 0.75 kilovolt per centimeter per bar. A colleague of ours from Novosibirsk, Buzolutskov, has seen secondary scintillation in the non-VUV region, in fact, ranging from the UV to the near-infrared range, and both above and below the electroluminescence threshold in argon. This secondary scintillation is concurrent with the electroluminescence and was pointed out to be neutral Bremsstrahlung due to the scattering of drifting slow electrons on neutral atoms. As said, it occurs below as well as above the gas de-excitation excitation threshold. Well, in the NEXT-White or NEXT new TPC, we saw a similar behavior for xenon gas in this case. And this motivated us to initiate a thorough, detailed study of this phenomenon in xenon. For that, we used a dedicated setup that we know very well and that allows us to isolate and control the several processes involved. We used a driftless gas proportional scintillation counter. It has no drift region to avoid or minimize attachment and recombination, and also a closed gas circulation system with hot getters to continually purify the xenon gas. We used alpha particles to increase the initial energy deposition in the gas. And the electric field in this gas proportional scintillation counter is established between the radiation window and the metal strips that are evaporated on the photomultiplier tube window. Well, the spectral sensitivity, as you can see, of the phototube ranges from around 150 to to over 600 nanometers. And the scintillation region or the scintillation gap is 2.5 centimeters. Now, in this proportional counter, the incident energy is absorbed near the radiation window, and the primary electron cloud that is formed drifts towards the photosensor under an electric field that is chosen by us. Well, to study the scintillation pulses, we used a Lacroix wave runner. And on the, you can see here two waveforms. On the left, we see a typical waveform for an electric field well above the Xenon excitation threshold. We considered the start of events as the instant that the waveform amplitude rises by 5% of the maximum height of the waveform. We see the secondary scintillation forming here and increasing as the electron cloud moves towards the photocathode. This increase in scintillation is mainly due to the increase in solid angle. We considered the end of events here and here as the instance when the center of the cloud, of the electron cloud, reaches the photocathode. Well, on the right, we see here, we can see a typical wave form for low electric fields well below the EL threshold. And we see here the S1 peak and the peak here on the right due to the scintillation that is produced at the anode strips where the electric field becomes strong. Now, here in between, we see a region where for those field values, there should be nothing, but we clearly see single as well as multiple photon emission. Well, in order to determine the scintillation yield, we selected a waveform region here in blue that is A, sufficiently delayed from S1 to exclude the de-excitation tail of the triplet state and also any after pulsing, and B, sufficiently far from the anode signal, which is dominated by diffusion. Then the average of the waveform integrals of a 4 millimeter regional interest was computed, and subtracting the integrated baseline, which is here in red, prior to the event. Well, here we see the computed number of photoelectrons per centimeter per bar, plotted as a function of the E over P values. Along with the experimental results, simulation values are also plotted as solid and dashed curves. The simulation reproduces the processes of both electroluminescence and neutral Bremsstrahlung emission for Xenon. The simulation includes the geometrical parameters of the detector, geometrical efficiency of the detector, and also the quantum efficiency of the phototube. And as shown, there is an excellent agreement between experimental data and simulation results. And this is a solid confirmation that what we are seeing is neutral Bremsstrahlung emission. From simulation, we can in fact obtain the absolute values for the neutral Bremsstrahlung yield. As we can see here, our results with the dedicated setup and those observed with the NEXT-White detector, they have the same profile, demonstrating that the neutral Bremsstrahlung emission is present in the NEXT-White TPC. And now concluding, we present an ambiguous identification of neutral Bremsstrahlung emission in Xenon, which is supported by a predictive theoretical robust model. there is a significant photon emission at fields well below the EL threshold, which is detectable with regular photosensors, from the UV to the near-infrared region, and it depends on the reduced electric field. For EL fields above 1 kilovolt per centimeter per bar, the neutral Bremsstrahlung contribution to the total secondary scintillation is less than 1%. But it becomes important in the buffer region of optical TPCs, not only in gas, but also in liquid, and for fields, electric fields, down to 100 volt per centimeter per bar in gas. So our work shows that the ample community of neutrino and dark matter experiments using Xenon should not ignore the effects of neutral Bremsstrahlung. And to conclude and to summarize, the detailed study and discussion of this whole work has been submitted for publication. Thank you very much. I hope you liked it.